Yeah, that's good. Just a minute so that I can share it. Indranil, can you hear me?
Yes, yes, I can hear you.
Okay. It has started. I'm sharing the link. You can start.
Okay, thank you. Okay, so this is the second part, and I think this will be. I'll just try to complete it in a short time. Okay, so I'll talk about the basics of scanning tunneling microscopy, and I'll just sort of connect it to the superconductivity course in a while. This is to start with, what is tunneling? Now, what is tunneling? To think about that, before that, let's think about a thought experiment where we sort of throw a plastic ball at a wall, and the ball sort of hits the wall and gets back to us. So that's the classical picture, that the initial velocity of the ball will be equal to the final velocity of the ball, if with the negative sign, because it's a velocity, and the wall will be just standing there doing nothing. Now there could be one way to think about that if you take a sort of ball and take over the wall, then what you have to do is to take it and sort of roll it along the terrain of a wall or a hill, and to go to the other side. So that's the classical picture. But one can actually think of the quantum picture in the same fashion, that for the quantum picture, one can just tunnel through the barrier. Now, what I mean by tunneling, I'll just come to that. This is just uh, cartoons to give you the idea that one can tunnel through the this barrier, and the idea of tunneling is just a consequence of Schrodinger equation. So one can start with a potential, which could be a potential like this green rectangle, and then one can show that even if the energy of the particle is less than the height of this barrier, one can get evanescent wave solution, which is the small amount of wave, small amount of uh, particle which can sort of tunnel to the other side of the barrier. And the tunneling coefficient one can calculate using mostly WKT approximation, that is proportional to the exponential minus kappa times d, where d is the width of the tunneling barrier. Now this expression is very important and useful, which I'll be using a lot. Now, so in quantum picture, if you throw a kind of a ball at the wall, if it's in the quantum regime, then the ball will tunnel through the wall. And that's the making of the STM, the scanning tunneling microscope. So Gerd Binig and Heinrich Rohrer in 1981 developed scanning tunneling microscope, and they got the Nobel Prize in 1986 for making the scanning tunneling microscope. So I'll just in one or two slides I'll just cover how the scanning tunneling microscope works, and then I'll proceed to the other parts. Now, if this is just a schematic, a cartoon of a short circuit. So if you have a metallic pin, or kind of a sharp anything object or anything metallic, and if you just touch it on your metallic sample and apply a voltage and measure the current, you'll see that the current flows through the circuit because you have a short circuit. Now one can just push away the metallic tip, or the metallic, this arrow, away from the your metallic sample, and in that case, if you apply a voltage, you won't see a current because they are sort of away from each other. Now, the idea between the scanning tunneling microscope is that you have a very sharp metallic tip, a pin-like structure, where the apex, or the head of the tip, has a few atoms and can have a width of a few angstrom actually. Now the idea is that if you take that tip very close to your sample, then if it's very, very close but not touching, then quantum tunneling of electrons will happen between sample and the tip. Well, the common materials which people use to make this kind of tip, even you can use it, are tungsten or platinum iridium. And what happens is that if this tip is very close to the sample, then the quantum tunneling happens, which is again the proportional to minus exponential minus 2 kappa d, is the distance between the tip and the sample. And then electrons sort of tunnel between the tip and the sample, and you observe a small amount of current. Now, since this amount of current is proportional to the tunneling rate, which is proportional to the distance between the tip and the sample, one can use this amount of current which is occurring because of the tunneling as a measure to scan the surface of any sample. Now this is a schematic of STM. I can go into a smaller details about these things. That the tip sits on a piezoelectric tube which is used to move the tip over sample, and because of the tunneling there will be some amount of current through this circuit, and that current is amplified, and then that amplified current is used to tell the piezoelectric tube as a feedback loop to scan the surface of the sample. And one can sort of generate topographic images, topographic data of the sample surface from the this measurement. Now the piezoelectric tube, well, looks like this, something like this, where one can have many electrodes, like to go to plus x, plus y, plus z, or minus z. And depending on the amount of voltage one applies to these quadrants, the tip can actually move like this, plus minus x and y, etc. Now, along with this, to build a STM, one needs a feedback loop, and the feedback loop depends on the fact that the tunneling current is proportional to the exponential with the distance between the tip and the sample. And depending on this formula, one can move the tip over the surface of a sample with different modes. One mode is called a fixed current mode. So what is done here is that the amount of tunneling current between the tip and the sample is kept at a fixed value, and to keep it at a fixed value, the tip has to go up and down following the topography of the sample. And because of that, what one gets from the feedback loop is the actual topography of the surface. So this is like this, that the tip has to go up here, somewhat up, because the sample has a up kind of a terrain here, and to a lower value here, and the tip has to go down to get a constant value of current. Another mode is called a fixed height mode, where the tip is held at a fixed height from the sample, and it's sort of moved along the surface of the sample. And what happens is that because the tunneling current again is proportional to the exponential uh, distance, the amount of tunneling current varies depending on the distance between the tip and the sample, and one can get from the value of tunneling current, just back calculate and get the height map or the topography of the sample surface. Now, this is a photograph of the scanning tunneling microscope at TIFR. This is used down to 350 millikelvin, and there's a superconducting magnet inside where one can apply 9 Tesla magnetic field. So this is the system which Professor Pratap Rajaudhuri and work on, and Shurojit is currently working on this system. So here there is a platinum iridium tip which is used to scan the surface of the sample. Now these are the the control units, electronics. I'm just showing some photographs to give you how it looks like. This is the cryostat, this is the control unit, this is some electronics. This is the variable temperature insert, or and this is the space. Okay, I can actually use the laser pointer here. So this is the point where the tip or the STM head is. This is the piezoelectric tube, and this is where the sample sits. One can scan the sample using the tip, which is somewhere here. And one precaution for STM measurement, one enemy of STM is noise. One source of noise is vibrational noise. To reduce vibrational noise, the whole this system, this sits on a vibration isolating table. These 4 legs have vibration isolating air cushions. There could be electrical noise coming from the mains power supply, like 220 volts. That has a 50 hertz noise. One can also check that, and one can minimize that by many ways. Another source is thermal noise because of the KBT, the energy, it gives some amount of noise to the system, and one way to sort of reduce it is to operate it at very low temperature, like 350 millikelvin, using liquid helium and helium-3, most importantly. So another way to get a good STM measurement is to have a very pristine sample surface. For that, in TIFR, a vacuum suitcase is used where the sample is made and transferred in 10 to the power minus 9, 10 to the power minus 10 millibar. Also, one can cleave the sample, get a very pristine sample surface for single crystals inside the system by, say, Scotch tape, for example. Another way to get a very good measurement, the best thing to have a sharp tip, so sharp that it has only one atom at its apex, at its head. Now, using these methods, one can get topographic images of the sample surface. Here, I'm showing you a topographic image of niobium diselenide. This is a single crystal. Here, the light regions have higher value, like top of the mountain, and the lower regions are kind of the valleys in this topography. So these are ups and downs in this whole surface. The beauty of this, beauty of STM, is that one can actually see atoms with it. So one can actually zoom a lot in this topography, in this sample, and so much that one can actually observe the electronic electron density, that up and down of electron density in the sample surface, on the sample surface. So this image on the right hand side is showing the atoms of this niobium diselenide sample. These are actually selenium atoms, which are shown here, and this small bubble wrap like kind of a picture. That's this, each of the bubbles, they're one atom. So this is the resolution one can achieve using STM. So one can actually see atoms. And if you take a sort of a line cut, if you go across the atoms and if you check how the height varies, so this is how the height varies. It's in picometer. And the lattice constant is also obtainable from such an image, which is about 3.3 angstrom. So the resolution is much better, about angstrom, and that's the beauty of scanning tunneling microscope. Now I'll just go into another kind of measurement, and that is where I'll connect the superconductivity course with scanning tunneling microscope in a proper way, which is called spectroscopy. Scanning tunneling spectroscopy, and this is actually beyond the topographic images I have shown you, beyond the scanning tunneling microscopy. So to start with, I'll start with what is called the Giever tunneling at t equal to 0. Now, to actually grasp the picture, let me tell you that the left side, suppose this is my tip, and this is the Fermi energy for the tip. The sky blue region, the sky blue part, is where the states are filled, electronic states are filled up to this red line here, up to the Fermi energy. And the right hand side, we have the sample. The Fermi energy is somewhere here. And we have a barrier in between them, which is just vacuum, which has a thickness, which has a barrier length of about d. So what is done is that one can vary the bias of the potential between the sample and the tip, and one can in that way vary the Fermi energy of one of the materials, and then check how much tunneling is happening. Now the transition rate for this tunneling, according to Fermi's golden rule, is given by this formula here, where we have this matrix element MFI, which is given in terms of the wave function for the tip and the sample. Okay, this formula here. Now, using the Fermi golden rule, one can show, from this formula, it comes straight away from this to this, that the current between the tip and the sample is equal to twice E times the transition rate, or W. But this 2 is coming from the spin degeneracy. And from this, it follows that I equal to this formula here with the delta function and summation. Now, in general, if the density of states of a material is this n as a function of E, then the number of states, or the D, is equal to the summation between some energy E1 and E2. This is for a regular continuum. But in a discrete vector space, the density of states is given as a delta function here, which is the summation over n delta E minus En. And for a certain amount, if you take the position space into account, then the wave function square also comes into play. So this is my number of states, density of states in real space, energy, and the real space coordinate r. Now, well, one can take the matrix element, one can write that in terms of just one Fermi energy, EF, by taking another Fermi energy to a reference point. And from that, one can calculate the transition rate to be equal to this summation here. The summation over the Fermi energy of sample to Fermi energy of tip, then this matrix element square, then density of states of the tip times density of states of the sample. Now, since we are dealing with energies here, one can choose the energies, the origin of the energy anywhere. So I am choosing the Fermi energy of the sample to be 0, so that the Fermi energy of the tip is set at some E times V. V is the bias applied between the tip and the sample, like the battery. Now, the current turns out to be this formula here. There are density of states of tip, density of states of sample, and the matrix element, and the summation is over 0 to EV. Now, this matrix element is actually the one which controls the amount of tunneling, which is proportional to exponential minus 2 times kappa d. This term has occurred to us before. We recognize this. So there could be 2 tunneling, one from the tip to the sample, another could be from the sample to the tip. So the total current will be this I122 plus I221, and the total current turns out to be this formula. Along with it, I have just taken into account the Fermi-Dirac distribution for t greater than 0. And this is the Fermi-Dirac distribution where it comes from, where it enters in the expression f of E plus EV for tip to sample, and f of E for sample to tip. If you just sum these 2 terms, then what we have is I proportional to the integral over energy. I have forgotten to write the dE term here anyway, and that's density of states of metal 1, density of states for metal 2, and then the Fermi energy difference. Now, this is the formula you will find in Dingham. And well, for a normal metal, the density of states is actually independent of energy over a small energy scale, and one can take out the density of states to be energy independent, taken outside. So if I have a normal metal and a normal sample, both tip and the sample are normal, then the current is INN, I normal to normal, and it's has a equation like this, where I have density of states of say metal 1, density of states of metal 2, both are coming out, and in the integral we have only the Fermi-Dirac distribution difference. So in this case, I can just call the integral to be this g of EV, and if I take the derivative of g of EV, this is just 1. Okay, so I can write this integral is actually integral over just EV. So my integral, which is here, is equal to EV. So the current, the normal to normal tunneling current, turns out to be constant. And I denote it by dINN to be GNN, and this is constant. This will be used as a normalization factor for other types of tunneling. Other types of tunneling like normal to superconductor tunneling and etc. But before that, how one can go from scanning tunneling microscopy to scanning tunneling spectroscopy, this is just a cartoon. That suppose in the left I have the tip and in the right I have the sample. Now electrons can only tunnel if I have some empty states in one of the sample or the tip. For example, here there are empty states in the right hand side or in the sample. So electrons are tunneling from left to right, tunneling through this barrier V0. Now one can actually vary the bias, I mean the amount of voltage I am applying between these two, and with that one can vary the Fermi energy of say the tip. So now also the tunneling will happen because it's coming from say the top part of it and there are some empty states in the right. If you vary it even more, then at one certain point of time there will be the Fermi energy will be less in the left, so there will be tunneling from right to left. Okay, now using this amount of bias and the tunneling current which is happening for metal to metal tunneling, the IV characteristics looks like this green line here. This is for a metal to metal tunneling. And I have already shown you that the DIDV is nothing but the product of the density of states of metal 1 times metal 2, and this is actually constant. So DIDV is actually constant for a metal to metal tunneling. Now the important part, the most important part is what happens for a normal to superconductor tunneling. Now for a practical purpose, I am taking the tip to be normal metal and the sample to be superconducting. This can be just the opposite, but this is the the practical and the experimentally used strategy. Now for normal to superconductor tunneling, which is written as INS, what I have is one of the density of states N1 of 0. This is for the metal. The density of states of the electron stays inside because it has a strong dependency on energy, near Fermi energy. Now I can replace this N1 by GNN, which is the DIDV for normal to normal tunneling. I can replace these constant factors by this GNN and N2 of 0. Now what it turns out to be that the GNS of EV, which is the differential conductance dINS dV, equal to GNN, which is the differential conductance for normal to normal tunneling, and an integral over energy of the density of states of the superconductor times the differential of the Fermi energy plus EV as with respect to EV. Now, this formula is extremely important, and we use it, extremely regularly. And from here, it gives us an experimental point of view of the BCS theory. How does it give it? Now, the density of states of superconductor from the BCS theory is this. For energy greater than the pairing potential, is E by square root of E square minus delta square. And for E less than pairing potential, this is 0. So one can put these values in the differential conductance formula and calculate how it looks like for normal to superconductor tunneling. Now there could be two limits. One limit is if kT is going to 0. At that limit, the differential conductance is just proportional to the density of states of the superconductor at an energy EV, and there are some constant factors. Another limit is for delta much greater than kT, and this turns out to be dependent exponentially on minus delta by kT. These two you can find again in Tinkham, these two terms and how relevant they are. What I will show you is that how one can get the superconducting density of states using this tunneling, superconductivity, normal metal tunneling. How one can get that is that if we have a normal metal and the Fermi energy is somewhere here, and at the right hand side I have a superconducting sample, and the density of states of the superconductor looks like this gray curve here, where the electrons are filled up to this point. This is mu2 and this is mu2 minus delta. So electrons are filled up to mu2 minus delta. So if one varies the Fermi energy of the normal metal, electrons will tunnel if I have mu1 which is higher than mu2 plus delta. That means if mu1 is somewhere here, then tunneling will happen. If mu1 comes down to some place here, which is about mu2 plus minus delta, then there will be no tunneling. But again, there will be tunneling if mu1 becomes less than mu2 minus delta, somewhere here. So depending on that, one gets the IV characteristics for a superconductor to normal tunneling looks like this red curve here. This is just drawn by hand, so don't take it seriously, but this one is done seriously. This is the differential conductance for normal to superconductor tunneling at different temperatures. Now the black curve is for 0.45 Kelvin and the yellow curve is for 7.75 Kelvin. This is done for a sample for a material which has a critical temperature of 8 Kelvin and a superconducting gap of 1.3 millielectron volt. This is just a simulated data, a simulated curves here. Now one can actually fit these simulated curves with experimental data, and from there one can extract the BCS superconducting gap and check how it varies with temperature. And how we generally find that for superconductors like niobium nitride, molybdenum germanium, or say niobium diselenide, etc., the variation of superconducting gap, the variation of BCS gap follows from the experimental to the theoretical prediction. I mean, the scanning tunneling microscope, scanning tunneling spectroscopy is an extremely useful tool to show that the BCS predictions are actually correct, not only correct, I mean, they're experimentally verifiable. Okay, so another type of tunneling can happen, which is for superconductor to superconductor tunneling, in which case the tip and the sample both are superconducting, and there one can write the current in terms of our GNN and the and the density of states of superconductor 1, density of states of superconductor 2, with the bias V inside. Now what it turns out to be that the superconductor to superconductor tunneling current ISS as a function of bias voltage looks like this blue curve here. It has one peak at delta 1 minus delta 2, which is about 2 minus 1.2 is about how much? 0.8, just about 0.8, and another one at delta 1 plus delta 2. So this is delta 1 minus delta 2, and this is delta 1 plus delta 2. So there are two signatures if there is a superconductor to superconductor tunneling happening. And if one sort of takes the derivative of it, one gets the differential conductance for superconductor to superconductor tunneling. And what one finds out, this has been described in TINCAM very well, that for the region between delta 1 minus delta 2 and delta 1 plus delta 2, that means this region, one has a negative value of differential conductance. This is just for interesting purpose. Okay, so with that, I sort of want to end my talk but since I can actually show you in 1 minute that how in TIFR vortices are observed using STM and how they are observed. Now you already know that vortices in superconductor have a normal metallic core, okay, which is surrounded by superconducting regions. Now, for a superconductor, the differential conductance looks like this red curve here. For a normal metal, the differential conductance looks like this blue curve here. Now, one can fix the bias between the sample and the tip to be somewhere at this value, where for a superconductor, we have a higher value of differential conductance, and for a normal metal, we have a lower value of differential conductance. So if one measures the differential conductance over the sample surface in presence of magnetic field for a type 2 superconductor in the mixed state, then the vortices which have a normal metallic core will have a lower value of differential conductance, which are shown in this brown points here. Okay, the brown points are the vortices where we have normal metallic core, where we have lower value of differential conductance, so they're dark. The light regions, the whiter regions, are the superconducting regions which have a higher value of differential conductance. That is why they are light in color. So this is a vortex lattice which forms this triangular lattice, hexagonal lattice, called the Abrikosov lattice, and that comes down from the Ginzburg-Landau theory. And well, this is for a metal, the material called niobium diselenide, a single crystal, and the area is 1 micrometer cross 1 micrometer. Okay, and the lattice constant is about 48 nanometer. Okay, so with that, I want to end the talk with showing this favorite photograph from TIFR. Okay, so any question?
I have a question. Hello?
Okay, if you have any question, please go ahead and ask.
Hello? Hello?
Yeah, let me. Hello?
Huh. What is the means order of voltage you are applying uh, in order to observe
So
properly?
generally, yes, yes. So generally, the superconducting gap is in milli-electron volt, generally for general materials. So the amount of voltage we apply is also in millivolt. Okay. So generally, we apply, say, for example, tens of millivolt plus minus to scan uh, the energy range,
Okay, okay.
order of magnitude. And actually, one can go even beyond. For example, one can, I mean, there's no limit. I mean, one can apply about 1 volt also, and then, but only we have to keep in mind that we should not go into the classical limit. If if suppose we are applying too much voltage, then we are sort of going to the classical limit, and then there's no tunneling. Just electrons are jumping through the vacuum. That's not uh, quantum tunneling, and then you don't have any kind of information which I have shown you. Those kind of information will only be available if you have the energy less than the barrier height, which is in the millivolt regime. Okay, any more question?
Hi, Indranil. So can you please explain your last slide one where you explain the vortex lattice?
Yes, sure. Oops. Okay, so what is done here is that the vortices have normal metallic core, right?
Sorry, your screen is not visible actually.
Yeah.
Yeah, now I can see. Yeah.
Yes. Right. So the vortices have normal metallic core, right? Normal metal. So for a normal metal,
Yeah.
if you are doing the tunneling experiment for a normal metal to normal metal tunneling, the differential conductance looks like this blue line here, which is just flat about the Fermi energy.
Okay.
Okay, just close to the Fermi energy, it's just flat. For a superconductor, this follows this red circles, which follows from the BCS density of states. So you have peaks at plus delta and minus delta, right? These are called coherence peaks.
Yes.
Now we can fix our bias at this value. Okay.
Okay. Okay.
Suppose this is about 1.1 or 1.3, okay, 1.3 millivolt. We can fix at this value. And then we measure the differential conductance over the full surface of our sample.
I see. I see.
Just differential conductance at a fixed bias. So that fixed bias differential conductance turns out looks like this because we have vortices. The vortex core have normal metal, and because they are normal metal, they have a lower value of differential conductance at
Yes.
this bias. There. lower. But the superconducting region has a higher value of differential conductance, so they are light. So this is how you observe vortices.
Okay, okay, I understand. Okay, thank you. And another small question. So you mentioned some technical aspect like how one reduce the electrical noises or something.
Right.
So can you please talk on that little?
Yes, sure. So, okay, this part. The main enemy of one of the main enemies actually is of STM is the noise, and the first source of noise is of course vibrational noise. Vibrational noise means suppose uh, you have a STM and someone just runs, uh, you know, just outside your door, or just takes something heavy and there's a vibration, and that vibration can actually affect the stability of your STM, and there will be noise. So one way to detach your system from that noise is to float it, or you have a different foundation completely. You can build a STM room in a desert, maybe there's no but one way to do is that to put the total system on top of tables like this.
Mm.
You can see, right, these tables,
Yeah, yeah.
and the legs, they are actually hydraulic legs. They have air inside, so this STM is completely floating. This has a huge amount of weight, and what more thing is used is that there are piezoelectric control tubes in
Okay.
these legs. So, and there are some what I call is a vibration analyzer. So whenever there's a small amount of vibration, there are piezoelectric tubes here which adjusts through a feedback loop the amount of negative movement you have to
Yeah, yeah.
kind of stabilize.
Okay. Okay.
Okay. Another source could be electrical, like the 50 hertz noise, which comes from the mains power supply. So one way to do this is, to uh, just think about the source is actually the 50 hertz. So, and it comes through the grounding of the system. I mean, there are three pins, one for the line, one for the neutral, and one for the ground. So what we do is we sort of take all of the grounds for all of the instruments and connect them to a single ground. Now this is actually
Okay.
very technical, but well,
Right, right. So like
grounding.
reducing common ground loops like a thing, right?
Exactly. So you sort of get rid of the ground loop noise, and that reduces the 50 hertz noise a lot. And the thermal is, of course, like, well, there are room temperature STMs, of course, but if you go to very low temperature, you will get to see more and more beautiful phenomena.
Okay, okay. And what is the typical scan speed of this deep?
So, for example, these images, so one end to another end. Okay, now not this image. I can give you a better value here. So one end to another end is 1 micrometer. So this takes about 2.5 seconds. Like 1 micrometer takes 2.5 seconds, and there are like 256 lines here. Okay, so I don't understand, I think, but let me just. So from this point to this point, the tip goes like this, and this is 1 micrometer, and this takes about 2.5 seconds. Now there are
Okay.
many lines here, like one, two, like this, and there are like 256 lines here. So this takes like 256 times 2.5 seconds.
Okay, okay.
No, discard. Okay.
Okay, fine. Take it. Thank you.
Mhm. Okay. Any more question? Or I can call it a day. All right. If there are no more questions, and is Rujit or Sal is here or no?
Hello.
Yeah. So you can just you are co-host, so you can just stop the YouTube live.
Okay. Oh, it is on sad hand. I have no option in the.
Okay. So
Oh, I can do
maybe
that. Stop live streaming.
right.